All right, howdy folks, and welcome to NESnet stream number 16. My name is Paul, go by InfiniteNesLives online. If you're watching this on YouTube after the fact, there's a time link in the description to the recap at the end, so you don't have to watch hours of me going through stuff. Otherwise, yeah. So we're just gonna keep rolling from where we did last time. We have a new board now. Oops, that's wrong camera. So our new board's got to go in FPGA, and it has a footprint for the ESP32 dongle, and then we've also got a SD card footprint so that we have some extra data storage and a means of getting data to chips on the board without an external programmer. The first hardware release of this cartridge is going to be with Action 53 Volume 4. I'm going to just have it as an optional thing for a few more dollars. People can get the hardware if they want to tinker around with Wi-Fi stuff. But so there's a second program. The game is going to be stored on the first 2 megabyte 3 volt program, and then there's a second 512 kbyte 5 volt program. So we need to control which one the NES CPU 6502 boots from, and what we're gonna do is actually put a bootloader ROM in the block RAM of the FPGA. So there's 8 kbyte of block RAM, and last time we got that added to our project, and we were reading back values from the block RAM that we put at 6,000, and it seemed that we were able to read back the values that we told the go-in memory tool to put in these. Oh, you can't see that. So the go-in FPGA designer has a memory initializer tool. You can just type these in by hand. If we have really short code, we could just manually transcribe our 6502 code into here and get it where we need it. But we're probably going to want to make it can also accept a memory initialization file, MI file, which is just a text file with each byte having a separate line in hex. So I don't know if we'll get to it today, but another thing that I want to do is make a Lua script or whatever that, hey, RetroStage, how you doing? I am back, finally streaming again after COVID hiatus, among other things. I didn't have COVID, but all the kids at home, as you well know, makes doing things like this a challenge, and we got to get this stuff out. So yeah, we're going to be tinkering with the so our mapper right now is, we've got the vanilla implementation of the Action 53 mapper, and we've just been manually selecting whether or not the PLCC flash is the program or the TSOP 48 is active. So we've been doing that in the verilog, enabling one or the other programs, and our block RAM is is currently at 6,000. So what we need to do is we need to create different modes of this mapper. When it first powers up, we want to put this block RAM in the last 8 kbytes of the 6502 address map, so that when the 6502 fetches the reset vector, it'll actually be fetching it from here, from our block RAM. And we'll have a little routine here, which will check if we have some specific button press on the controller. If we do, then enable the whatever mapper we decide we want the development cartridge to be in. I don't know yet. Maybe we'll just start with MMC3 or something. For the 5-volt program, and so it'll enable that and then jump to the reset vector in program. I guess to some degree, maybe we should have the block RAM mapped at 6,000 and at would it be E1000? Yeah, CHR RAM only. We could. There is space for. There's space for a CHR-ROM on the board right here. This board has it. The CHR-ROM there. But I don't really see much value there from a dev cart perspective. It's got 32 kbytes of CHR RAM. We've got, well, the 2 megabytes for the game are restricted. Right. Action 53. I mean, I guess it always kind of annoys me how mappers are. Like, mappers are always defined as having CHR RAM or ROM or either. Some mappers that never had it, they're like, well, this mapper only has CHR ROM. Well, it doesn't change anything for the underlying memory that's under there. But yeah, maybe INS 2.0 gives you some leeway there of defining things as, I think it does, as having CHR RAM, even though it didn't initially, or traditionally, I should say. Yeah, brings cost down. I don't think it's really going to get made use of. 32 kbytes of CHR RAM is a decent amount, and we've got tons of ROM available. And I mean, part of the thing is in general, I kind of want to set this up as a configuration that's fairly generic, and if people like, I'll probably at some point release this board not as Action 53, right? Once everything's, so the goal is to kind of sneak the hardware out there for people who want it, and the ESP and the SD card and all that stuff won't be enabled when it ships. They'll have to have an INL Retro program or dumber to update the firmwares of all the different parts on the board. Because basically, if they don't have a programmer, it really limits how I can help them with new updates or figure out what's going wrong. So require that to even enable the hardware, and I don't have to have all the firmware rock solid to get it out the door. And once things are more stable and working, people have good luck, then I can release a version of this board that doesn't bother with the Action 53 Volume 4. It's not a game cartridge, it's just a development cartridge, or you could buy it to release a Wi-Fi game or whatever. But kind of the default would be something like 512 kbytes of PRG-ROM, CHR-RAM 32 kbytes, and then the block RAM in the FPGA is going to provide 8K of PRG-RAM. Yeah, so the kick lockout chip is this tiny little guy down here. So right here, it's not wanting to focus, but this is my STM8 microcontroller. It's a TSOP 20 footprint. That guy is kind of my secret weapon. So it's here. The STM8 microcontroller. So when normally this is just operating as a kick lockout chip, CIC, so the console doesn't reset the blinking light. But I'm using it for a number of different things here. Right now, it's already in use as a JTAG controller of sorts for the FPGA. So I think, where are they? Here? No. TCK. And our other TDI. All these signals. TDO. TMS somewhere else. Anyway. Yep. So the FPG, this is a GW1N-1. So it's their smallest FPGA. 1152 LUTs, 800 some flip-flops. It's got 72K bit of block RAM. But it's actually, so it's 9 bits wide. So the bytes can be up to 9 bits wide or multiples of 9. So basically it's 8K byte by 9-bit bus, but we don't really have this NES isn't going to be able to easily access that last bit. Yeah, it's a lot more. It's like 5 times more LUTs. The Mach-XO 256 I've been using on this board had 256 LUTs, so we're over 4 times more LUTs. And the Mach-XO didn't have any block RAM. This also has 12K byte of user flash. It has a PLL. It has effectively the same number of I/O, but under the caveat that you have to dual purpose these JTAG pins, which isn't the worst thing in the world. I need some pins to go between my microcontroller and the kick microcontroller. So it has internal flash, configuration flash. One of the annoyances, though, is that by default, left to its own devices, the GoWin will try to boot from an external SPI flash connected down here to these pins. And it does that because by default, the mode pin has a pull-up resistor, internal pull-up, and if it's high, it'll try to boot from that external SPI flash. I don't have a SPI flash there, right? I'm just using these for different program address pins and such. So you could just like ground this pin, or put a pull down resistor. Yeah, exactly. I don't get it either. I don't know. You would think that, I mean, I get that there's probably a lot of designs out there that do default to an external memory, but why? I mean, the chip can't boot. Like, the chip won't configure itself without that pin grounded at power up. And I tried having the microcontroller take that pin low at power up, but it takes a few microseconds for the STM8 microcontroller to come out of reset, and by the time that happens, the FPGA has already tried to configure itself from the X. It already sensed the high level of the mode pin and tried to boot from the external SPI flash and failed. So what I've had to do then is that when the STM8 microcontroller boots up, it takes this pin low, and then one solution is you take this reconfigure pin low, and that'll cause it to reconfigure itself, and now the mode pin's low and it'll boot. But I wanted to use this pin for something else. It's kind of annoying. I would have kept it connected to the STM8 microcontroller, but this pin is output only, so that limits its abilities as a multi-purpose pin for other things. So I was like, well, you can issue the reconfigure command via JTAG. So that's what happens. The microcontroller takes it low, issues the reconfigure over JTAG, and then the FPGA will boot from its, or I say boot, but reconfigure itself from the internal flash. But if you want to use these for other things, you have to also enable JTAG. I forget the logic here, if it's default enabled or what, but the microcontroller controls this as well. So then after it's all running, now I can put logic in the FPGA, and kind of establish my own. My plan is something that's similar to a JTAG controller, but my own version, and have different registers that the NES or the INL Retro can communicate to the kick via there. The kick can boot up and tell the mapper tell the FPGA which mapper to select at boot and stuff like that. But yeah, so comparing to, I've only really used for Xilinx, I've only used ISE, this looking guy. I haven't really used the, what's it, Visa or something, some sort of V. Yeah, I've only used the old Xilinx Webpack for the 9500 series. Yeah, Vivado. I've fired up Vivado because I thought I had to, and then realized I could still keep using the old stuff. I've used Lattice Diamond fairly heavily. I'm very happy with Go-In devices, especially for the value that they provide. In this market segment, right, the low end FPGA, the tools are very basic in their abilities, which is kind of a good thing. That's like one of my biggest gripes, honestly, with Lattice Diamond or ISC Design Suite's pretty basic, especially just for an FPGA. But using Quartus and stuff like that with Altera, there's like, to get into deep settings and stuff, I don't know, it's like learning. You can spend a lot of time learning how to do what it is that you exactly want to do in that design suite. Whereas Go-In, there's not a ton of buried things. It's pretty basic, but the devices are pretty nuanced and the documentation is so-so. I've had to get some help from the FAE to figure some things out. It took me a while to figure out when you dual purpose. So you go in here to, here's where you can dual purpose all of these configuration pins. Yeah, it is Chinese company. They do have North America, or at least the US, but I would assume, I would guess it's Canada or North America in general. They have European segments as well. They don't have, from what I gather, you know, there's only like the team is pretty small outside of China, but there's also not a lot of users so far. I don't have much trouble getting direct help. I've been pretty, in reality, I've had better luck with go-in FAEs and stuff compared to Lattice, and I've never even talked to an Altera or Xilinx FAE. I just always feel like, you know, I'm just a small potato, you know, I'm not a big enough customer to really warrant their attention, you know, but I've gotten a lot of attention from the go-in guys. So it took a while to figure out, you know, you do purpose this mode pin. Well, then how does it exactly behave? The documentation doesn't really say, right? and figuring out these pull-up resistors were there. Like, the documentation talks about some different things, but like most of the stuff that I figured out was just by me probing myself. Yeah, it's there's, you know, there's enough documentation there to know that this is like a thing. It explains the mode pin and how it works. But when you're like, how does it work when I disable it? I mean, what does it, and there's like auto boot and all this stuff, and like, well, what? So, you know, there were some challenges figuring out. The other problem I had, the other gotcha, is when you do get it configuring itself from internal flash, it's pretty slow. It actually takes like somewhere on the order of 17 milliseconds, which for most consoles is fast enough, right? The 6502 doesn't come out of its power on reset to like 20-30 milliseconds. So if it configures itself in 17, you're good. But I found that a front-loading console, yeah, for the N60, I don't know how fast the N64 boots, but I can imagine when you disable the kick on a front loader, the console actually boots up faster because the kick I guess it's a microcontroller, controls the reset circuit of the 6502. And when it's disabled by lifting the pin, it boots in like 15 milliseconds. So I was like 2 milliseconds short. And I'm like, you know, comparing that to Lattice devices and stuff, they're like 1 or 2 milliseconds. I'm like, why is this so slow? Like, and I did the math on the 44 kbytes of configuration data, and it's like, this is insanely slow. Why is it so slow? You know, this is a deal breaker for me. And the FAEs helped me figure this out. You go into the bit stream and the download speed. So for whatever reason, the slowest possible 2.5 megahertz is, and I didn't like download speed. Well, download speed of what? Like, is that for when you program the FPGA over JTAG or what? No, that is the, what's this wake up? See, like, I don't know what this is. Maybe this is something to do with the mode pin. in the default. I don't know, but if default's 0, then that would be internal. So I don't, it's like I can't find anything. I haven't actually looked for wake up, but so that's where like the documentation doesn't really help out. You've got to work directly with an FAE. But you select 24 megahertz, right? 10 times faster, or almost. And I think the data sheet says that 24 megahertz is the fastest. I tinker around, and I think like 30 or 40 works, but 60 doesn't. But 24 is plenty fast. And so just selecting that option, and now it boots up in a few milliseconds, which is great. Okay, problem. But so it was like a month or so of going through all these growing pains, but like now that I'm through them and using it, like I'm pretty happy. I've had pretty good luck with the IP core generator to do block memory and the PLL, and I haven't really got into the user flash. It's pretty complicated, but the documentation seems okay. Like I think I got a decent chance of getting it to work. So yeah, it is unfortunate that like hopefully some distributors like DigiKey or Mauser or somebody starts stocking their devices soon. Just getting samples is kind of a pain. There's I think, what is it, Edge Electronics is who I work with to purchase the parts. They have a bunch of devices listed here. I don't know where. I used to be able to just buy them. Yeah, I use Arrow a lot. They don't know the Edge is, as far as I know, Edge Electronics is like the only distributor in the US or North America for that matter. I don't know why they're just talking about them. Oh, so they got some dev boards here, and they got devices. This is basically our device. So you can supposedly buy them, but there's no stock. I think when I went through, they had stock of some devices, but like this site is nothing compared to, Mauser, Arrow, DigiKey. Like you can't search by if it's in stock or not. You're just like, oh, I want this device. Nope. Yeah, they're pretty well priced. You do well, so you don't in Canada. Hold on a second. You do have the Chinese import tariffs in the US. The Cyclone 4 is $12. Jeez. These, I assume that you're not talking about the board. But yeah. That was, so I had been eyeing Go-In since around the beginning of the year. But knowing that all the growing pains I was likely going to go through, 144 EQFP. Yeah, they do have a 144 pin. That's their biggest TSOP, or I guess TQFP. so I have my eye on them, especially with the block RAM that they have and everything, but not really needing it for my like MMC3 board and stuff like that. But I had been eyeing them, and then Lattice announced end of life on their Mach XO chips, and I was just like, all right, well, here we go, got to get this done. So I made up a prototype and worked through all those challenges, and I'm like, okay, let's just go for it. So now I'm using them as my primary device when I needed something greater than like MMC1. Anyway, yeah, that's my impressions of GoWin. So I've got it set up right now to where the INL Retro can reconfigure the GoWin over FPGA or over JTAG. That took me a lot of time to figure out. They actually have some decent-ish documentation, but it doesn't. Some timings are ambiguous, and there's a lot of gotchas there. So, I got that figured out, and the INL Retro communicates to the Kick microcontroller through the Kick pins to reconfigure the FPGA over JTAG. I don't want to completely rely on that at all times because my oldest kazoos don't have connections to those pins. You could add some bodge wires to get that support. And with this Wi-Fi, we can get data from other places. But yeah, so I need to figure out. I got everything figured out to reconfigure the internal flash, but it doesn't work for the boot data of the block RAM. So I'm still using my external JTAG programmer right now. So I need to develop that still, but yeah. So let's what are we gonna do first here? I'll get my music going. JTAG instead of serial. Well, the FPGA really, I mean, natively JTAG is the only thing that's supported. You can't configure a FPGA over serial. So the GoWin FPGA will configure itself over like SPI, and I think maybe I2C, there's like some parallel interface that it'll also can be configured from, but oh, I see. Yeah, and Lattice Mach XO2s have different options for SPI and I2C to reconfigure the internal flash. But for the GoWin, as far as what's documented, the only way to program the internal configuration flash is via JTAG. So that's the only option that I have. And yeah. All right. So yeah, so this can still be possible, right? We can, I mean, ultimately, the only option I really have is for to reconfigure the FPGA is via JTAG, but I'm doing it with the STM8 microcontroller. And so that effectively allows me to get the data from wherever. It just goes through the hands of the microcontroller. So that is one of the goals, is to use the SD card and have a means for the STM8 microcontroller to get configuration data from the SD card, or to get it from Wi-Fi, anything that it has available to it. So right now, the communication protocol that I have, right, yeah. So the protocol I have now is using the kick pins, and it's basically a SPI protocol. It's not synchronous. Well, it has a clock, but it's everything's bit banged because it's just over the pins that I had connected. But so it's not crazy fast, but it's fast enough. So that's one of the things. My ultimate goal is, when we release this, is that you don't necessarily need a 9NL retro. Once the firmware's mature enough on the microcontroller that can get configuration data from the SD card or from Wi-Fi, then as long as you can program an SD card or connect to Wi-Fi, you can get new data. And that's not just the configuration for the FPGA. If it had a bootloader of sorts for the program, right, then the NES could reflash the program. So we could have a little updater ROM in our block RAM that pulls data from the SD card or from Wi-Fi, and the 6502 would reprogram the program. So then you could put a new build of your game or whatever you're developing without even unplugging it from the console. So all of this stuff we're doing will kind of build to that. So what I want to do is I really want to get us booting off of the block RAM for the 6502. We also need, so we're going to boot from the block RAM and then select which program and then jump there. So we need some different modes, but I think ultimately what we want is multiple mod. We want some different. We want each mapper to be its own module. So maybe let's try to break that out. Thinking about this though, right now I have the block RAM as an internal module of my mapper module. But really, we want to think of that as separate. So it's almost, from the mapper's perspective, the block RAM is external to it. So we'll have two separate mapper modules. We'll have the Action 53, and then we'll have whatever the dev mapper is. Probably just MMC3 or NROM or something to start with. and then we'll boot in this default setting where there's basically no mapper. It's NROM using the block RAM. We'll have our bootloader there, select Action 53 or the dev ROM, and then jump there. So let's see if we can basically I don't want to change any of the It's snowing here too. I woke up this morning to let the dog out and it started snowing. We got a little bit of dusting on the ground. We have although it's above freezing now. We got 37 Fahrenheit here. So I think this is basically where my mapper code starts. So let's go to the bottom here. Action 53 TSOP. Yeah, just below freezing for you. So I should put it in a different file, but I'm going to keep it in the same file, and then once we get it all separated, we can tinker around with different files. So although I'm thinking about maybe just make a whole new project. So let's do this. Let's get a new make a Wifi folder. I guess that's what we want. We'll call it GOROM A53V4. Select our device here. we need to set our default stuffs here. Dual purpose everything. We'll do a binary format, and it actually does both of them. Okay. So I got my configuration and the Action 53. Copy those over, but let's change this to all right. We need, I'm kind of curious. We'll just, I know it works, so we'll just go through the block memory. Single port block SRAM. Yes. '8192. 8-bit wide. So it's going to use all 4 of our block RAMs, and it doesn't need any extra logic to implement that. Oh, you can change the name here. Okay. Add the files. So I think we can synthesize this now. That's good. All right, and our programmer tool. So we're using this guy. Erase program verify. Run that, and I think we have the what do we call it? Wi-Fi. Yeah, so the T-stop flash. Okay. Yeah, it's good. Let's just power it up. Make sure that it's working. That's good. Yep. we have the entire ROM, so that's the 2 megabyte flash is enabled. So now, oh, and we can test this too. It was apparently not working to read our, oh, you know what? We didn't set up the configuration or the memory initialization. So if we, let's copy this one. So save as, oh, I haven't. Is it, do you know whose device it originally was? Alliance is always basically redoing somebody else's ST. Yeah, so this one is, I wish this part was select, it's 48 pin. They got enough pins, but oh no, it does do. So the 29F used on your 5-volt Game Boy board. I've been looking at, where's the data sheet here? Am I blind? Do they not have a data sheet? Maybe I'm just not seeing it. No. That's a Micron part number. It must be Micron. My old employer. They do lots of Micron legacy. Yeah, okay. Because Micron's always had these parts, but they've always been expensive. Nope. I'm pretty sure no. You're saying ST Micro? I don't know if ST Micro ever. SST is microchip. Yeah. I think SST was purchased by Microchip, and Microchip purchased a Atmel as well. But the SST is the flash that a lot of us use for the program. But Micron's always had this. I was aware of Micron having this part, but it was always unreasonably expensive. But now that they're manufacturing it for, I guess the question is how much does it cost? This isn't overly impressive, but when you're short on space, and I don't know how just because that's the online price doesn't mean you can't do better than that. But the part of things is like a Game Boy board and stuff, you don't really have room for level shifters all the time and 5-volt native parts. It's worth the extra cost. So did I save this? No. File, save as. Save it as bootloader. So let's add that initialization file. We don't need this. Add a file. Open. Oh, I think you have to because if we look at our verilog file here, our generated verilog, it doesn't have any initialization. So we got to go back here. Got to do this every time. Whoops. 8192. 8. Yep. Provide the memory initialization file. You'd think there's an easier way to do this, but I guess it's... See, now it's gonna overwrite our now it has our initialized values. So to some degree, you don't really have any choice. If I knew how that bit mapping worked, it would be nice to have the script copy from a binary file straight to the verilog, but I don't know if it's really worth trying to figure that out. Gotta go through that step every time we want to update the block RAM. So now if we synthesize and reconfigure, we should be able to. So here we're just, my script just reads the block RAM. It's all 0. That's the default initial value. ST and Micron. Oh, what are they doing? Oh, this was 10 years ago. Right. Intel, Francisco. Yeah, so Micron acquired Mnemonics because when I worked for Micron, we owned Mnemonics as well. And I think that's where these parts originally came from. I think these were originally Mnemonics parts, and Micron acquired Mnemonics mostly for their NAND flash. That was the main focus of Micron with Mnemonics, but then they still had some of their NOR flash. And so I'm not too surprised that Micron passed off their NOR flash to Alliance. Yeah, that's my understanding anyway. Because I worked for Micron from 2012 to 2015. But ST Microelectronics announces agreement. Well, what did ST Micro? Did ST Micro own Mnemonics? I wonder if that's where the relationship is here. I'm not going to sit and read the whole article, but. So ST Micro entered agreement with Micron, in which Micron will require Mnemonics. Yeah, so I guess ST Micro owned Mnemonics and then sold it off to Micron. Yeah. Because I haven't seen anything. It'd be interesting if ST Micro was. I mean, they're all in the semiconductor industry, but I haven't heard any specific partnerships between ST Micro and. But then it's confusing because then there's SST, which is not ST Micro. SST is owned by Microchip. It's like all these companies using the same 3 words for their name. Okay. I think we ran this. I don't remember. One more time for good measure. All right, so now if we read up all F, is this goofing me out? Is it actually getting configured? There we go. Okay, so we're reading our configuration data. That's good. All right. So I want the Action 53 mapper to be tied to the the 5 volt. I'm sorry, the 3 volt TSOP 48. So let's try to separate these out now. Take all of this. Put it down here. Now, we need to wire up all of our, we need to get all of our input and outputs to this mapper. So it's going to be a lot of these. So here's what I'm thinking. So from the mapper's perspective, I'm just going to have data as an input. If I had an output, I would do it separately. But because the block RAM is going to be separate, then we don't need it. To some degree, all of these inputs that aren't really needed can be cut. Let's really cut these. Let's just leave these out for now. And these. We do need so what all do we have? A chip enable, an output enable, and then a write enable. I think that's all we really need. So we can kind of think about this from this mapper's perspective. We have the external W RAM on the, well, it's not actually on this board, but this one has it. Ours won't. But we can think about this block RAM as an external chip from the verilog and module perspective, and then our top module will control when the data bus based on those. So I'm just going to cheat with always asterisks. Oh, let's do this. So my mapper or my top module would create an M2 effective signal, which has the rising edge delayed. That way, you can sense. That way, the ROM select delay is not a problem. So the mapper will have that available to. Here we're sensing 6,000 using M2 effective. So when that's high, then ROM select will be valid. So I think that's where we have our we need to get these. So we're not doing that block RAM data control inside the mapper anymore. But all of this code is written from the perspective of how I normally think about a mapper. So it can think of itself as when it's activated, it can effectively think of itself as all that's going on, but there's another layer on top. So we got to connect all this stuff now. Whoops. So we have our module, but now we need to invoke it. So action 53. Say game mapper so the module's name is first, and then what we want to connect to it at this level is in the parentheses. So like that. They're both called the same thing. Most of these are going to be the same name. Sometimes it's best to actually say what's getting connected here, in case they're not always there. We aren't using these. So the outputs we're going to have to multiplex. For the first step, I guess we don't have to multiplex them. We could just connect them, make sure it's working, and then multiplex them, I guess. So this is where verilog gets tedious. It's connecting things up. But that's kind of nature of the beast, I guess. Especially if you're it's too easy to make mistakes. Hey, GeoTrek, how we doing? So right now we're just gonna connect everything as this being the only mapper, and then we'll add in the dev mapper or master boot mapper. And multiplex to pick which one's active. This is the external WRAM, even though we don't have it. So right now we are all the way down on the hardware level. We're writing verilog. Give you a quick overview here. So this is our NES cartridge board. We've got this module here it's a little Wi-Fi module. It has a small microcontroller on it, and there'll be networking code on here. Lots of provided libraries and such to do all of the network level communications with Wi-Fi through your router and everything. But we have to have the NES 6502 CPU needs to be able to talk to this guy somehow. It has limited connections and doesn't directly bolt on to the NES bus. So we've got a mapper, which is a memory controller slash. This is how we're gluing everything together. So this FPGA is what glues the glue logic between our module and the 6502 on the NES. There's a bunch of different stuff in here, and it's also controlling a lot of different stuff. So it's controlling all of the memories on the board and how they're presented to the NES. And we write the code that's on here in Verilog and synthesize it into hardware inside the FPGA. But because the board that we're working on right now is being released as a game and as a development Wi-Fi board, there's two separate modes. And so normally it's just going to boot as a game. So when you power on your NES, it plays a game. If you want to develop a Wi-Fi game for the NES separate of that game, or your own utility or tool or whatever, then that's going to be on a separate memory, and the memory controller can be in a different mode. So we are wiring everything up so we haven't even really gotten to the network aspect of it. We got to get the groundwork laid for the 6502 to be able to execute from the code that we're writing. So this is all Verilog here. Hardware level stuff. There is there are some C or C++ translators, or I forget the names. So most of the time, if you're describing hardware inside an FPGA, so hardware description languages are HDL, not cholesterol. Are written with Verilog or VHDL. I use Verilog. It has some C-like syntaxes, but I don't remember what the names. I think there's a specific one for C++, but the kind of the gotcha with those is if you're used to C or C++ or whatever, you write them sequentially, right? The processor is executing your commands one line at a time, or that's how you can think of it. The compiler might do some optimizations to not quite exactly be like that, but program, you can effectively think of it that way. But when you're dealing with actual hardware, it's not sequential. If you have a AND gate over here and an OR gate over here, they're operating completely independent of each other. You change the inputs of this one, there's they're not inherently related. So it's not like and this and then and this. If inputs of both of them change at the same time, then they're both going to change at the exact same time. So if you're thinking in that sequential manner, you can create a lot of problems for yourself. And that's where some of the tools that try to translate that are like, well, they're supposed to be figuring that out for you. And I think things like that are usually written by people who like those languages. And I mean, I like C, but when I'm writing C, I'm not in a logic frame of mind. When I'm writing verilog, I'm describing hardware and I'm thinking about things in a hardware manner. So, and there might be some Rust ones out there, and not that those things like can't work and aren't useful, but they're kind of the wrong tool for the wrong job, in my opinion. I'm already comfortable with verilog, so I use verilog when I need to describe languages, and I write C when I want to program a microcontroller. So right now we're just it's kind of a pain, but connecting everything up here. Last two. So these signals are the level shifter control, separating the 5-volt and 3-volt portions of the board. Let's just get rid of this. We'll bring those on if we need them. Okay. So if this is all proper, I think the main thing though is let's take these out here. And this block RAM is I think it's gonna throw us for a loop here, because it was inside our Action 53, our mapper module, and now we're making it outside, and I have a bunch of all the signals with the same exact name. But it's so let's just look at chip enable. So here I'm instantiating them, and then we have the block RAM module has it connected, and the Action 53 module is connected to those, but the Action 53 is a output. Yeah, so output block chip enable, and then for our block RAM, it's an input. So I think that's going to work. It might supposed to be a wire instead of a reg, but let's just see if we can synthesize it, and hopefully GoWin won't puke all of our... Oh, you know what though? We didn't... What about the data bus? Because... So our top module has the data bus as bidirectional. And block RAM has it as an input. The buffer has it as an output, but only when B output enable is enabled. Yeah, I think that'll be okay. There goes nothing. Some errors. Oh, I probably... The last one shouldn't have a comma. And what about down here? Same thing. Let's try again. Expecting statement. Line 447. Did I? So I got my module. I have all of my signals. Always at maybe I shouldn't really have oh, maybe I don't want this. Yeah. I don't want this. So we have these are all the signals, register signals inside our mapper module, and then we have always blocks for our logic. And I might have an extra end here. Let's try that. So all of these did it get mixed up? Which is our top module? Did I? Because we still have them here. And we have our Action 53. Oh, wait a second. What did I name the module wrong? Action 53 TSOP. Let's try that and hopefully we didn't kill our configuration file. That is one major annoyance with the GoWin has been if you change the input and output pins in the verilog, it like completely destroys your configuration file. So you have to be like super careful with that. Reassign every single pin on the FPGA. Okay, I think it's all right. Let's check the floor planner here. Make sure we didn't have anything like that happen. This stuff looks pretty good. I think it's just a deficiency of the software. Like I found that you can do it, but you have to like be very careful. The best thing to do is save a copy of your configuration file. But if we like, so what I think will like break it is if I just change one of these pins to an input and change the logic, it would just completely obliterate my configuration file and automatically assign things wherever it wanted and start all over again. So yeah, here's my note to myself. Changing pins and go on EDA. Make sure everything's good. Reset properties and save pins you want to change. So I think if you want to change this to another, if I wanted to move this pin somewhere else, reset properties, which will clear all this out to default. And save for the pins you want to change. Comment out all the pins you want to change. So in here, comment them out. Resynthesize and reload floor planner shouldn't have deleted all the other assignments. Yeah, so if you want to, so basically remove the pins, synthesize, add the pins back in, synthesize again. So yeah. So then you can, so once the pins are gone from the floor planner, then you can add them back into your file, refresh this, and then assign them. Yeah. I spent a lot of time just assigning pins. But I think we're good now. We don't care about that. Let's make sure we can. ID code mismatch. Come on, meow. There we go. Yeah, I mean, it could be a glitch. My guess is it's just a bug on, I mean, not a well handled case by their software. So it seems like we're good. We reconfigured. Let's see if we can read our block RAM. Doesn't look like it. We're getting something though. I wonder why. Let's see if it boots. My guess is no. Oh, we did boot. So, wait. We've got the Action 53 ROM. The main ROM, the 3-volt flash ROM. So that is working. But we're having some problems with our block RAM. Oh, did I? Yeah, that's. Let's see how. Let's check up on ourselves here how everything's connected. So, the top module data. So the block RAM has data as an input, and then there's block RAM data out. I thought I moved this. Maybe we didn't save it. Yeah. So this is on our top level module. We have wires coming out of the block RAM going into our bidirectional buffer. So this buffer is effectively there's a tri-state pin and a out for the output driver on the data bus pins. So because the block RAM is the only thing that provides data outgoing of the mapper, we just have the wires directly from the block RAM connected to that buffer, and the only time we have the FPGA drive the data bus is when we've got the block RAM output enabled, and that is enabled by our mapper. It's an input for the block RAM and output from the mapper. Which is enabled here. So when the mapper decodes that the block RAM is enabled due to addressing, for writes, output enable high, write enable low, reads the opposite. Otherwise, it's disabled. So I think because we didn't have this wire at the right level, that would have caused problems. I'm surprised it didn't give us, and maybe we got some errors. Oh, look, it removed instance of the block RAM because the output didn't go anywhere. So if we would have been paying more attention to that. I don't know why we're getting these weird values. It's consistent. Maybe it connected something here and that was the default value. I don't know. Let's try again. Now that we did that at the right level. I just blasted my switch off of there. I'm just going to resolder that on there quick. It's kind of my hack to program the FPGA externally. I've got to hold the STM8 kick and reset. I'm just going to burn this back on there quick. My little bodge wire. I try to make you can see it, and I left it on the wrong camera setting. Wasn't that exciting anyway. All right, hopefully this is working now. Well, here's the problem. Is really just a quick. There we go. We got our right values now. It's I really just need to patch my STM8 code to when it's not driving the JTAG signals at boot, that it releases the JTAG signals and lets them float, or just runs a pull up. Because what I've got going on, right, so the microcontroller is driving the JTAG pins, so I can't drive them externally, which is what I'm doing here with this cable from my JTAG programmer, an old lattice board that I repurposed, the FTDI chip, because I had a hard time getting a JTAG program from these GoWin FPGAs, but the dev board was just an FTDI chip, and I'm like, I wonder if I just connect the FTDI chip on one of my old lattice breakout boards instead of to the CPLD that's on there, just connect it to the GoWin, and it actually worked. Later on, I ended up getting my hands on a actual GoWin JTAG programmer, but so my quick fix is just to have a reset pin here for the microcontroller, have a little switch that holds the microcontroller and reset, and then those are tri-stated, and it's a lame workaround because I need to get this project up going again and change that code, but a quick cheat that is not very consistent. But anyway, now it seems like we've got it working. Let's make sure it's still playing. Yeah, that's good. Good enough. So, I think I'm going to take a quick 2-minute break here. Refill my coffee, use the restroom, and then we're going to connect up our dev mapper. I think what we'll do is just do another copy of Action 53. Because that's what I already have flashed onto the other chip. And we can copy the module all over again. And then once we have that working, we can switch it over to MMC3 or whatever. That'll be a little faster. So, yeah. I'll be right back. So for now, let's copy our Action 53 TSOP module. Action 53 PLCC. So this will be the 5-volt memory. Which was this code. Comment out this code. So the mapper module is almost identical, except it enables the 5-volt flash, disables the 3-volt. And the data direction is different. It doesn't, this one enabled it whenever we were reading from the program or the block RAM. Here, it's just the block RAM. I guess what should, to some degree, this could be on the level above to just say if the Pro chip enable is enabled, or the TSOP 48 is enabled, then decide what to do. But anyway, so I'm curious how much extra logic we end up using here. But to some degree, I may not actually have it. Well, we'll include them both. So all these connections are the same. It's just a different module. But we have these outputs are being driven by multiple things now. So it's only this first chunk that's input. Everything else is output. So the inputs don't have to change. But the outputs do. Well, ultimately, we want these mappers to be completely independent of each other. So let's just mux it up. So we'll have A53 for these signals. And then we'll have these as dev. Ah, come on. All right, so all the outputs for the modules are wired up. Now we need to mux everything. And we have to create the signals. So I think these can basically be wires. It'll be pretty easy to change it. I think my bus is going to be wrong. I think you do it like this. Opposite way. Yeah. So these are all our A53s. Now we need a bunch of dev wires. Now we need to mux them all. What's going to be the best way to do that? We could make a make a mux module. It's going to be kind of like this module. Hey, Stakaneko. How we doing? We're creating a big switch to select between our two different mappers right now. So we're making it easy, and they're just both two different copies of the Action 53 mapper module. One enables the 3-volt big 2 megabyte, and the other one's a small 5-volt dev-ROM. And then once we got these all working, then we can change the dev-ROM to whatever we want, the mapper. So mux this is just going to be a 1-bit mux. So now we go mux 1. Oh, we got to create. I don't. It might be easier to just do this in one big always block, less code. Maybe let's just do it like this. I think this is going to be. I don't think it's gonna. I don't know. Sometimes it doesn't like having modules that aren't used, and then it, because it's the last one and it's unused, it thinks it's the top module. So if I'm not using it, I'm not going to put it. So we're going to say 0 is game mode, dev mode. And we'll just assign everything. I think we can kind of copy these. is. I should be doing more per line here. So CI-RAM chip enable equals okay. I think that's good. You just gotta change all these devs to 53. All right, so now I'm just manually setting mapper select to game mode or dev mode. Later on, we can control how this bit or byte, whatever this register that's controlling this. We can do this with software. But just to make sure our verilog and everything is good, let's duplicate instance game mapper. Oh, dev mapper. So that's configured. It should be in game mode. Let's make sure we can read our block RAM. That looks right. And we'll boot it on the CRT, and we should have the full Action 53 ROM with all the games, and that looks right. Yeah, that's loud. Anyway, that's working. So we didn't actually, that was what we had working previously. But now it's through our giant switch. So let's change our mode. So we'll synthesize this and flash it up, and we should have the smaller ROM, 5 volt. Block RAM still good. Boot it up here. And that's right. We only have half the games. So now that we have everything all wired up like we want it, to select between the two different mappers, can create some logic to select this on the fly. Instead of hard coding this to which mode we're in. The other thing we can do is, part of me wants to do this now. Part of me says it doesn't matter. Is we could put a different mapper in place of the dev mode. If we went ahead and slapped a MMC3 mapper in there, we'd be able to better test the program. Although, and I only really say that because flashing MMC3 is a little cleaner than Action 53. Let's just go ahead and do it. I think it'll be fairly easy to do. Mostly copy pasting. So we'll do TN-ROM because it's CHR-RAM. Don't need all that. And then we can Yeah, whatever, we'll just stick it all in the same file. Okay, so we have a couple things that we need to block out and change about our inputs and outputs. So these are still going to be inputs. We added an M2 effective. Just comment these out so it's easier to read. Axe these. I guess I can leave these inputs and they just don't get assigned. But comment them out. And then I didn't do anything for those. And we're not doing anything with those. And we need to add, whoops, add our block RAM signals. So now I'm going to take all this out. Ooh, we need we do need an oscillator because we do some filtering for the PPU A12 signal. But I think the only thing I'm using this M2 shift for is creating M2 effective, which I'm providing externally. But the A12 filtering needs a clock, so let's put it let's just put it here. So up here. All right. So it has a clock source now. Everything else, I think, can just stay. The scanline counter is a separate module. I'm gonna hack all this out. Just make sure I don't break anything in the process. So the scanline counter is a separate module down here. Okay. Got a PLL, another code, but don't care much about that. I think that'll be good. Oh, we need to change our WRAM control over to block RAM. So this W chip enable is actually just an internal signal because it's not actually on the board. And then here, I'm controlling the WRAM external signals for the chip on the board. But we're going to instead, we're going to internal block so if, well, so let's disable the external just by setting it this. So, and then we want block chip enable to equal W chip enable. So that's when the block RAM is going to be enabled based on our internal signal. If our WRAM is enabled, our block RAM output and write enables are going to be set based on read write, otherwise they're going to be disabled. So I think that's going to be good. I'm not 100% on these I was curious about, but it looks good. So let's see if we can synthesize it. We'll have the dev mapper selected. It won't boot, but we should be able to reflash it with our test ROM. Let's see how it goes here. All right, let's see. If we just pass our mirroring test. Okay. It looks like it. And we're getting our manufacturing ID. I don't have the test ROM I need, I guess. Let's get this guy copied over. Which folder? I'm in the release folder. No. Okay. Okay, we're just gonna flash 512 KB test ROM. And this will actually exercise the WRAM for us. Let's double check those files. I might have a header problem. I think my dump added the header and I don't have the header. Yeah, they're identical. But let's make sure we don't have. Yeah, we've got an extra line in the dump. So the dump included the header. Oops. But it looks good. So let's test it on the NES here. So it didn't actually, you can't really see that, can you? Maybe if I make it bigger. That's out of focus. I don't know. You can kind of see it. Program missing is what it's saying on this line right here. So it seemed, and we did have that issue. We tried, oh, there it's better. Test our program with INL Retro, and it wasn't working. So I don't know. To some degree, we can figure out that problem later. Seems to be readable. Not writable though. Let's maybe just look at our code. See if we see any obvious problems. One thing I wonder, so in the mapper, when we assign the block write enable signal, this is an action 53 mode. So we take it low when it's chip enabled, the clock's enabled. Because the tests that we did, they're higher up here. But we did a write test here, and like nothing actually wrote. Where did I put those? Oh, I think it's in the, not the TSOP. Yeah, here it is. So I'm just writing to the first 2 bytes of block RAM, and nothing changed. It's not like garbage got written. Nothing. But what did I do? So this was a different MMC3 project that I had working with block RAM, and it was writable. Well, this is the one thing that I changed it so that the write enable signal was just driven by the prog read write if write mode was enabled. Read only mode, it was just stuck high. Otherwise, there was read write. Let's just try copying this. See if it changes anything. Oops. I think I just used W chip enable for the, yeah. Could be a data level shifter problem. If it's reading the value and then writing it back again. But we'll just try this, and if it's not the problem, then we'll move on. I don't want to get hung up on this for too long. So this is what I had before, is I always enabled output pin, but I don't really want to do that because then then we're always driving the data bus. So maybe let's do this. So if the chip enable, if the you know, we're our mapper is enabling WRAM with the chip enable pin. It's just an internal signal. We'll set the block RAM output enable to the inverse of prog read write. So it'll be high for reads, low for writes. So it'll be the opposite. And then the write enable pin will either be high, it'll be stuck high if we're in read only mode for the WRAM. Otherwise it'll be the prog read write, low for writes. And if WRAM is not enabled, then it'll be, both those signals will be high. So let's just give that a slightly different logic here. And I didn't actually make, MMC3 has write on or read only mode for the WRAM. I wasn't actually doing that. I'm guessing the test would have still worked. Okay. Yeah, still missing. Whatever. Well, ultimately we only need to be able to read it for now. I'll get into later, maybe off stream, why I can't write to it. So, but we have things mostly. So we have our test ROM flashed on to the prog ROM, and we have our game, our Action 53, flashed on to the 3 volt, the 2 megabyte program. So this is kind of a good test case. We'll be able to easily tell what's being booted from. So our game is on the 2 megabyte 3 volt ROM, and then our test ROM is on the 5 volt 512 kbyte. And it's properly sensing TG-ROM with CHR-RAM. So things mostly seem good in our 2 different mapper modules. What we need now is effectively a 3rd mapper, because we need to map that block RAM into the top address section of the 6502 so that it'll actually boot from the block RAM. And then that mapper needs to have a register visible to 6502 so it can make a write to enable a different mapper, and then one of the two that we have selected here, and then jump to its reset vector. So let's get in the right file. So on our top level, so I'm thinking all right. Take care, man. Have a good one. Stay warm. Enjoy the snow. Catch you next time. Will do. So here's my thought. Is kind of have this effectively as a I'm just going to have the so I still have that. Yeah. This memory map is kind of nice to look at. So normally you got 32 kbytes of program, and then from 8,000 to FFF, there's no 10,000 because there's no A16. So it's kind of dumb. But anyway, we've got right now we've got the block RAM down here. Apparently it's not writable, but we seem to have been able to read from it, which is all we need for our bootloader anyway. And we've got either our MMC3 program there or our Action 53, depending upon which mapper we have selected, enabling which ROM. But every time the board powers up, I want to put the block RAM basically in this entire section. What I really want to do though is execute from the block RAM down here. That way, so the block RAM will be in the reset vector. We'll jump down to it in the 6000 to 7FF. We'll perform, the 6502 will perform its checks of the controller, and based on its decision of which ROM to boot, it'll write, well, we can just put a register at the entire range here, 8,000 through FFF. It doesn't really matter. We only have the one thing. This bootloader ROM will write a value there. That'll change which mapper is selected. But since we're executing from block RAM down here, I guess we might have problems with MMC3 because MMC3 can have the program completely disabled, I think. Or is it always readable? Yeah, we might need to change the default state of the program on the MMC3 to get this to work, because what I don't want to happen, I mean, one option is to execute from system RAM down here. I'd rather not touch system RAM at all. Just used our block RAM on the board. If we probably don't need any RAM, actually, we can just use internal registers. But if I enable the MMC3 ROM, my block RAM should still be here, but if it's disabled at power up, then I'm not going to be able to read from it. The 6502 can't read from it to execute my code to then jump to the reset vector. So, although we might need RAM to perform our jump. Anyway. We can change the, so this mapper select register, this register I only want to be able to be written to once. So it should start up with both bits 0. We'll use the lower bit for this. So the upper bit, or I don't know if it really matters, but since we effectively have 3 states, 3 mappers, our boot mapper, our game mapper, and our dev mapper. So if map cell 1, that way this logic can kind of always be active on the top module, but it won't have, it only have effect on the first write. Yeah, if this is only for boot time, could you have the selection delayed, as in once the register is written to, it waits long enough for the CPU to read the jump instruction? Yeah, that would be an option. It'll consume some logic though to implement that delay. So it's kind of a complicated option when it comes to hardware, because now we have to have a counter and we got to figure out how many cycles we want to wait. It counts the cycles and then does it. So yeah, that it would work. So if mapper select upper bit, yeah, it's one of those things where, like, it seems simple in theory, or if you ran like a microcontroller or some sequential logic, like it's a lot easier to do that type of stuff, and it's not necessarily hard to do here. It might not be a bad option. It's just that in the end, I don't really care about the startup state of this program bit. I mean, this mapper is just a placeholder right now anyway. So we could have it start up enabled. I think normally it starts up disabled for MC3 just to protect the battery RAM. but we don't even have battery RAM right now, so register hasn't been written to yet. So if ROM select yeah. Well, the thing is I need to some degree have a better idea of what's going on once we actually start writing the assembly. So our jump options, so we have to make this right based on the D-pad, and that will enable either so before the write happens, right, we have our block RAM visible in the upper address space. So if we read the reset vector before then, we're just going to get our own bootloader's reset vector, which is we're going to send it down to 6,000, even though it's the same 8K byte quintupled up five times in a row. Once we make the write to this register, then we'll get the proper program enabled in this space to jump to the reset vector. There's no reset command that, opcode that we can run in 6502, and we can't really do absolute because we don't know what that reset vector is going to be, especially on the it might not change on the game ROM, but on the dev ROM it could be anything. We don't know what the developer is going to create, so we have to read that 16-bit reset vector. We're going to have to store it in RAM, and then we'll be able to do jump is the only indirect opcode, right? So we actually do need 2 bytes of RAM to do this. It might be, I guess to some degree, the easiest solution might be to execute from, that's probably the most bulletproof thing, is to actually execute from the RAM in the system. I just hesitate slightly on doing that because then when the dev ROM or the Action 53 ROM starts, this RAM has been sullied. It's been manipulated by us, and ideally, without in a normal situation, when the game ROM or the dev ROM is handed execution at reset, this RAM is completely random, or whatever their console happens to start up as. If we change that, it's not virgin anymore. We've put known values there, which could, if they happen to rely on that, then... So that's kind of where I like the idea of we only mess up our own RAM on the board, and if they're relying on that, then we don't really have much. We don't have much option anyway. So we can use 2 bytes of RAM. We're gonna have to be able to write to them. I guess we really do need the block RAM to work to do that, but what we can do as a placeholder is actually look at the reset vectors from the program. Once we get the WRAM working, then we can actually implement the indirect. But one step at a time, I guess. There's lots of little gotchas that are going to get us here. So if the upper bit's clear, we're going to allow writing to it. And if ROM select is low, aka and read write is low, so the ROM is making a write to 8000 through, we're just going to put this register in this entire space here. That way we can have the block RAM read only here and write only. Well, read and write in 6000. So if we write to this space, then we're writing to the register. If we write to this space, then we're actually changing the block RAM itself, and we'll have to do that because we're going to have to put an indirect jump in there. But we'll say map select equals well, let's just do this one. Map select 1 equals we'll set this to 1, and map select 0, we'll say that's data bit 0. So we can use this upper bit to control the programs. Most of these I don't care about, like the CHR-RAM, the program address pins, the CHR-RAM address pins. I don't really care about these. I just care about the chip enable signals for the program. So we're going to have to leave these out. So the upper bit, if map cell 1 is 0, we're in bootloader mode. Else game or dev mode. So when we're in game mode or dev mode, we need to set these based on the mapper selected. But in bootloader mode, we're going to say the 5 volt program is disabled and the 3 volt. We're going to disable both of them. If this is going to be based on so here we're gonna, so if it's 0, we're gonna have this logic. I'll end up putting more stuff here, but for now, let's go on dev. Like, one of the things that I want to make sure is that the game ROM is write protected. I don't want there to be any way for us to write code for the mapper that makes the program, the 3 volt where the Action 53 is stored, writable. So to do that, we'll move that control to this top level here. But I guess the other thing is these the block RAM control signals have to be here as well. So block RAM chip enable. I've got to do some address decoding. Let's just take all this. Why do I have the... Oh! I think I found our bug for the block RAM. This is supposed to be up here. Without it, else one line is going to have else block output enable is low and then or high, but here we're always assigning write enable high. How many times do we have? If you just ignore your bug for a while, then you find the problem. So it was wrong in the action 53, which would explain why we had that problem. Initially, what about our MMC3? So here it looks right. I don't know. That would have explained when we did our tests back here that it was why it was not writable. But it doesn't quite explain why our MMC3 is not writable. Anyway, we might do some testing with INL Retro before we test with the 6502. So this here, so we'll create a WRAM chip enable signal that will enable for the 6000 range when A13 and A14 are high, M2 effective is high, and ROM select is high. So we'll enable that. And we'll say then if W chip enable is low, I should be like writing, I don't know, I just if else are so much more less likely to create bugs here. So if chip enable is low or ROM select is low, B chip enable is low, else it's high. So this will enable the block RAM all the way from 6000 and above. If WRAM chip enable is low. It's in the 6,000 range. We're gonna set it to writable. Here's a write being performed if read write is low. Here's a read being performed. Otherwise, read only. Well, we're gonna keep this low, so write enable is gonna be high, but output enabled needs to be set to ROM select. We don't want bus conflicts though. So if it's a write, we'll have them both high. Or anywhere, really. Writing to anywhere in the 6502 address space. Anywhere except for the 6,000 and 7,000 space. But here, we're performing a read, and so the block RAM will get enabled if we're reading from 8,000 and above. And writes won't be. Something like that. So I think this stuff, it's kind of hard to read, but it's a lot of if else. Let's synthesize it. One thing I'm not certain of is the startup value of the register. I set. I know this works on Lattice. At least I think it does. When you instantiate the register, the reg, you can set it to 00 here, and this will be the startup value. Integer size out of range, 213. Oh, a 2-bit binary, not a 0-bit. It's at least parsing that line. That's good. Maybe it'll do what we want. Okay. Oh, look at applying initial value of blah to instance flash select. It gives a, oh, look right there. So if we, let's go look at these other ones, see if, did I actually, yeah, see, I gave these startup values. And it's telling us that it's actually doing it. So that's cool. Let's hope that it actually does it. One thing I should have checked. I wonder how much usage we got. 155. I don't remember what our Action 53 and MMC3 were by themselves, but it seems reasonable. I think MMC3 is 100 something. We could open those projects and look, but let's just go ahead and try to flash this, and then we can use the INL Retro to perform some reads and see if we're reading what we think we should be for the ROM spaces. We don't have a, we haven't actually put a bootloader in yet. But we can at least check to see if the stuff's behaving like we think it should. So that configured. Switch over here. Let's try to run. Let's run this. So this should test to see if the MMC3. So MMC3 mirroring sense passed. The IRQ counter seems to work. But when it tried to read the manufacturing ID of the flash, it just got Fs. I would have expected it to not be Fs if block RAM was there. But it seems like the MMC3 is there and the 5-volt ROM is not enabled. So because we had it start up as 0, well, oh, you know what though? I bet So part of the thing is if the INL Retro performs a write, any write to the 8000 range, it's gonna put us in whatever mode we think. My scripts probably do that. I have to write a new script. Our Action 53 is it's getting a whole lot of Fs. Where's the... Oh. Okay. So let's... So we don't want to do... any sort of anything, any sort of writes. Let's just put this here. Okay. Let's try to read from the reset vector. I should put that in a variable. Whole lot of nothing. Oh, wait a second. Our our level shifter control is inside the mapper. And you probably don't want it to be. I bet the level shifter isn't getting enabled. Let's try this though. See if writing something to the mapper gets anything different. Doesn't seem to. A whole lot of nothing. Although it only allows one write. Hey, there we get something else. So what did we write? We wrote 1. 1 is dev mode. So in dev mode, we should be reading the reset vector of this guy, which is correct. It jumps to FF or F0, F1000. So it might be kind of working there. Now, when we read from block RAM, we're still getting Fs. But whatever. That's so. Let's try game mode. So game mode, we seem to be getting a whole lot of nothing. And we shouldn't be able to see we're stuck in game mode, the broken game mode. Even though we so our logic is somewhat working here, because it won't, even though we're making the write to go into dev mode, it's stuck in this broke. But if I unplug it and plug it back into power cycle and try it, we get game mode, and it's stuck there. This write isn't going to change anything, because I'm really just writing to, when I uncomment this, I really just write to the MC3 register. So we got something working here. This seems to be working. At least the upper bit is starting up clear. Any write to 8000 sets the upper bit, and then it's stuck there. And which value we write does seem to matter, except in game mode, it's just we can't read either program. So let's these we're going to want to change. In reality, we can control the level shifter outside of the mapper. Although you'd think, since we get game mode selected, that we should still be able to read the program or RAM, the block RAM, but we never actually got that working, and it might have been a level shifter problem. Oh, I bet it is. Hold on. And more reason that we need to not control this. See, my MMC3 mapper has it stuck as input only. So that's the bug. That definitely is keeping the program from working in MMC3 mode. If we fix that, TN-ROM test might pass. And we fix that other block RAM bug for Action 53. Okay, so let's do this. Let's just not let these mappers control. Let's just control this on the highest level, or level shifters. Oh, I need it on the highest level. Level shifters, man. Oh, and this is going to be broken. Remove that comma. So this is gone. This is TN-ROM. Okay. Same with data editor. So now we get to control it. On our highest level. Shouldn't the second always block depend on both bits of map select? So you're talking about this one. Here I have map select 1 instead of both. In reality, well, usually these, when it does depend on more than what you put here, the tools will be like, oh, you forgot to include this signal. We're going to include it. So to some degree, you can like be lazy and just put an asterisk. Hey, tools, figure out what signals you need and include those. But in reality, it's more than, you're right. It does depend on map select 0 also, but it also depends upon these signals too. So it's like, I probably have a warning for incomplete sensitivity list. I'm pretty lazy about that stuff. Yeah. Reference variable, blah, not in sensitivity list. It's just that's the annoying thing about verilog. And to some degree why just writing an asterisk is easier. In practice, it doesn't really seem to matter. The tool figures it out for you, but shouldn't really be relying on that. Let's just see if we can yeah, if you set first, let's see. If you set map select 1 in that first reg-write code, it might not realize it needs to redo this after you change map select 0, but then also remember they'll both change. Yeah, well, and part of the thing is like the idea of like it needs to go redo that code. Like the reality of it is that logic that gets synthesized is always active. So, you know, from it's not sequential code, right? So we're describing hardware that's always running, and really this is just, it's supposed to, the idea of the sensitivity list is to give the synthesis tool an idea of, hey, what signals are dependent upon what other signals. It's obvious that the thing that I want to happen, and so that's kind of, I think, why like early days of verilog, it like required that, and then this heavily depends upon the synthesis tool, but it's the most correct answer would be to include everything that I should be including CPU address, M2 effective, ROM select, map select 1 and 0, and all these signals. But yeah, it's a good thing to be cognizant of, but I get lazy. Same thing up here. And in some ways, this is probably better if I'm not gonna. I mean, it's like it's to like write every single one of these signals up here. It's just like so incredibly verbose. What it really is. I think system verilog might be better with some of that stuff, but anyway, let's write our level shifter control. Now, I think we can have this level shifter control kind of be completely independent of everything, just from the mindset of we know what things are behind the level shifter. The 3-volt flash and the FPGA. And we can tell when they're enabled based on the signals, the memory control signals. And so if we just base everything off of that, then I think we'll be okay. So if some case else so I think the default is 0. Where's my MMC3 code? Yeah, so always, if they're both low, then the level shifter is enabled and the direction is into the cart. So if P, so what are the, when is it not into the cart? It's not into the cart when we're reading from the PRG-ROM or the 5-volt or the 3-volt flash. So if in all of those cases, the 6502 has got to be on a read cycle. So if prog read write equals 1, and then I'm just going to write these out separately. P48 equals 0 and P output enable equals 0. Because I think, right, the code always enables that. Here it's always enabled, but the output enable signal is dependent upon ROM select and read write. So in this case, if the block RAM's enabled and the output's enabled, we're going to read from the cart as well. Else read from elsewhere. We don't, if it's reading from the 5-volt flash, we don't need to enable level shifter because it's on the other side. Now this, I don't 100% like this. Yeah. Thanks for that. So I usually have this level shifter stuff a little bit different from when reading from the TSOP flash because I've had problems before. Here I set the direction if I was reading from the flash. This is basically the same logic above. But then if I'm reading from the cart, I only enabled the output if M2 was high. But that's really only, I mean, it's dependent upon ROM select anyway. I think it's whatever. We'll just go with it for now, see what happens. if our mapper select code isn't working, I'm curious to just force the mapper select code. Hey, we cut a bunch of logic. That's not always a good thing. Let's just flash it, see what happens. So this right now, game dev mode. Okay, that looks good. That looks a lot better. Let me open the ROM. Just verify. Here we go. Check this reset vector. So 73E1. That's different. Oh, you know what? It might. This mapper is kind of funky. It might not have this one selected by default. Let's just search through here for, it would be C2 8D hex all. Okay, that's not in the proper location. That's not the end of a bank. That would be, though, if it has the second to the last bank selected. What if we read? I don't think we need these. Oh, yeah. Okay. C. Let's read from C and D also. So 60A9. Yeah. For whatever reason, that's what's selected. That might be. I might have an issue there based on what that mapper starts up as. I thought the last bank, let's look at what the action 53, the default, I think. Power up state At power on, the last 16 KB of PRG-ROM is mapped to C1000 through FF. The rest is unspecified. Mapper state unchanged at reset. But I wonder if we're having an issue. We might, when we perform that write, we might be changing the state of the mapper to select a different state of this multi-mapper anyway. That, watch out for that because that could be a problem. So let's try this. Okay. So in game mode, we are getting things as we expected. Now, we're not actually reading the block RAM though, but it is possible that that's because the program might not be enabled. It probably defaults to disabled. So let's see if we can so we need to write to A1000 with the most significant bit set. So it's enabled in read mode, or read and write mode. So A1001, write 80. If we do that, hey, look at that. We read from our block RAM. Let's try to write to it. So okay, it looks like it's writable now. So now here's the other question. If we don't do any writes, power cycle it quick, we should be able to read our block RAM. Tummy's not very happy. So if we don't do any writes, this will be FF00, which is our initial values of the bootloader. FF in the last, F0 here. So that's a good sign. We might I'm a little concerned about that situation with the, well, here, let's do this. Let's look at the Action 53 mapper. Well, technically, because we might be able to just change where we write to and not break the startup value, because we really haven't changed the inputs to these mappers. So when we write to 8000, we're writing to our register select, and we're also writing to our mappers. Now we could add extra logic to prevent that from happening. Or we could, I'm in the wrong code. So we have everything start to set in all of these things. So reg select starts up at 3. This is 5000 range. We're gonna, if this defaults to 3, then we're gonna change the outer bank when we write 8000 here, and we're gonna be selecting bank 0 for the outer bank. So what if we try this? We'll just rewrite. If we do that, I think that's still the same here. I mean, the reality is we don't have to start up in this with reg select set to 3. We could start it set to 0, so then we're just changing the CHR bank. I don't know if that's actually going to. But the most significant bit of the program is clear. It must be, if that's what we're reading. If this ROM is doubled up. If I search for this, I only find it once, and it's here, smack dab halfway through the ROM. So this is the address we're reading from, 7F1000 instead of, or 7FFFF instead of here. I wonder. Oh, thanks for the follow, Kidarp. How we doing? Let's just flash this quick. I don't want to get too hung up on this. We seem to have fixed a number of things. New to the channel, so we nothing. What'd I do? Oh, my wires came disconnected. Those matter. So we're trying to build a Wi-Fi capable NES cartridge here. I haven't worked on it for a while. We just started working on it again. And I'm gonna do an early release of the hardware with a game release that we got coming up. Let's try this quick. Same stuff. Oh well. Let's see if it actually, if it boots like it's supposed to. So we're writing a lot of verilog here. I'll show the board quick. So this is my latest NES cartridge board here, but we've got a little Wi-Fi module that it's only got a few pins connecting to our right now we're programming this guy. It's an FPGA, a GoWin FPGA, and this controls, basically it's kind of the control center, the brains of the whole chip, although it's mostly just logic. So we've got 2 different ROMs for code for the NES CPU. We're storing the game on this 2 megabyte ROM, and then this is the second ROM that's available that is just for development purposes. So this is going to be released as a game. This is the This is volume 3 release that we did on my older circuit board. We did this a few years ago, and the guys over on NESdev and a number of other places online, they make their own games, submit to competition, and then we have so many. Yep, that's right. 826601, exactly. So we're putting the boards together for release of the next volume of games, and I've kind of been working on this Wi-Fi thing for a while now, but I was like, well, there's already have majority of this hardware on the board. If we throw on the ESP, maybe some of these guys will. I have a number of people keep asking me, hey, when can I get my hands on the Wi-Fi hardware? And I'm like, well, I kind of want it to be semi-final before I go selling anybody anything. But if we have the basics working, it only costs a few dollars to add the ESP, and we've also put in an extra micro SD card slot on the back. And so kind of a sneak release of the hardware, and let people get their hands on it if they want. First and foremost, it's just a game release, but secondly, a Wi-Fi NES development cartridge. So we have to select between those things and control which memory the 6502 CPU inside the NES boots from. And so that's what we're working from right now. Once we get that working, then we can develop code for the development ROM and more. I've done a lot of work on the ESP code and stuff, but I got to get this basic stuff done first so that we can release it and then update stuff with my INL Retro USB programmer after the fact. So I'm just gonna, that didn't actually seem to fix anything, changing that default register, but so this is default writable. Oops. So I'm going to do this. If this is, so if the map, if this register is set to 1-0, then it's game mode. And if it's 1-1, then it's dev mode. So we can hard code these things to just kind of test all the other logic. Make sure that the Action 53 ROM will actually boot when this register is set to what we think it should be. So we'll test that quick. If this is mostly working, this might be as far as we get today. Let's see what we get here. We get the same thing. So I don't know, maybe that's, for whatever reason, it's not the last. I don't know. Let's see if it boots. No. We're pretty sure we know why, though. Some sweet colors. And it might just be our assignments of the address pins for whatever reason. Let's test MMC3. Yeah, so FPGAs they're tricky. They're kind of their own beast compared to everything else. My goal with this is to make it so that if somebody wants to make a NES game using a Wi-Fi connected cartridge, they don't have to really understand how an FPGA works. But they are a lot of fun when they behave themselves. So it did go into the dev mode like we wanted to, and our program is working now. So it's able to read and write to that program, which is actually block RAM inside the FPGA. That wasn't working earlier. It is now. So let's see. Let's check our upper address. If it's so the ROM itself is 1 megabyte. If we read the reset vector, we're not getting this byte, or this, this is the reset vector, but this is actually what we're seeing. If we go back here we read the reset vector, C28D, or I guess it's Little Indian, so 8DC2. Unless I'm backwards. Yeah. So we're reading this, which tells us that A19, address 19-bit, is clear when it should be set. So we have 22. So the top module has A12 through A22, and our wires are A12 through A22 for both the Action 53 mode and the dev mode. We could specifically go through and assign all of them, which might be a good idea. A22 through A12. That's where I said, right? Yeah. 11 bits. here's our mapper, A22, A12. So A22 through A12 or A18 through, yeah, and then down here all these other modes. Let's do this. Let's explicitly say what we're connecting there. I don't think that's really going to change anything though. It can't hurt though. Let's force that back to game dev mode. And earlier in the stream we did that. Unless oh, look at this. This should be if map select 0. That might be our problem. The lower bit. Who knows which, that was probably saying if both bits are set to 0, which wasn't actually the case, because the upper bit would have been set. I bet that's our problem. So let's try that, see if that fixes our problem. Hopefully it does. Why is it not? The wire's coming loose again. We could maybe try a stab at a bootloader ROM. Make a really short bootloader ROM, typing it in by hand into the memory initialization file. Things start acting up though. I'm not sure I have enough patience. So we're selecting game mode. Hey, that looks right. Let's make sure it boots up. Yeah. So there's our 2 megabyte game. Well, really, it's 1 megabyte doubled up because I'm using volume 3 instead of volume 4. Just because that's what I had flashed on there. Okay. Okay. I think we figured it out. Let's not hard code that anymore. Well, and this is really we set these, we're forcing these modes because the upper bit is set. All right. We'll just test it with the INL Retro. And if it seems our logic is working, we'll give a shot at hand typing some assembly. Some machine code, I guess, really. Okay. So we flash that on there. What we think is close to working config. So our INL Retro is going to do this. It's going to, I don't think we actually need this. So game mode, and then it's going to try to read the reset vector. That's our telling that, hey, we have, it should be the same as here. Yep. Now, we'll write dev mode, which is 01. Now, the first time this won't actually work because it's, you can only write to that register once. So we power cycle it, unplug it, plug it back in. Now we're reading F1000, which is the reset vector of the dev ROM. What we should have done is read before we write, because if this should be the bootloader vector. Now we won't actually read it because we already wrote to the register, so power cycle it again. Yeah. So FF0, or really the reset vector was 0FF, which is based on our memory initialization file. Where'd it go? Okay, I can't see it. Right, so this is the startup values of our block RAM. We wrote to select the dev ROM, and now we get 0FF, which is the reset vector of our test ROM. Okay, so it seems like it's working. It won't actually work in the NES though, because at power up we'll end up jumping to 6502 address, Little Indian, so FF0, which is just going to be a bunch of zeros. So we have to make our own. So reset vector we're going to have as 006,000. So we'll jump to CPU address 6000. The reset vector's up here at the top, but our block RAM is going to be down here. Well, it's going to be it's going to be mirrored up 5 times. 1, 2, 3, 4, 5, because it's 8 kbytes, and we have a 40 kbyte from 6000 to FFFF. So our reset vector is going to be 6000. Little Indian. That is, wait, hold on a second. Make sure I'm getting my vectors right. Oh, that's actually the IRQ vector. Reset, so it's NMI is FA, FB, reset is FC, FD. It seems weird to me. Like, if they're at the top, why wouldn't they be last? Bah, I don't know. Okay, we caught that bug before we... So that's actually the reset vector, is the second to last 16-bit word. So that's going to jump to here. What do we want to do when we get there? We're going to do an LDA. I'm just going to write this all by hand. No assembler. LDA. Immediate. So it'll be A9, and which value we're gonna do? We'll do let's do game mode, because the block RAM isn't gonna be disabled by default. Although we could fix that, but anyway, we'll do 0, 0. So that's gonna be, that'll write, or no. All we did is LDA 0. So now we have to do STA. STA absolute 8D. Whoops. 8D and the address. Little Indian. We'll write to 8000. Okay. So that will write to our mapper register. Now we want to jump to the reset vector. Now we well, you know what? Let's just go for it. Although maybe we should pad in some no ops here. But for MMC3, it's just really not going to work, because as soon as we make that right, if it defaults to the RAM being disabled, we lose execution control. Although what about this? Hold on, let's do this. I think this might work. So the way that we have this set up is that we're writing to both register or both mappers always. I don't have any sort of blocking to prevent you from writing to the MMC3 dev mapper or the Action53 mapper. I just always allow those writes to happen. It's just they have no effect. There's a mux on the output of all of those mappers. So if when we make our write to ROM to select. We may have problems just because the way the 6502 is fetching the next opcode. Maybe not though. Because the write's not going to happen. So what we're going to do is we should be able to make our write to the program protect register, which is A1001. Our bootloader register doesn't care about the most significant byte or bit. So let's write to A1001 instead. And let's LDA 80. So we're going to have the most significant bit set. So we're going to enable program on the MMC3 mapper. And instead of writing, we're going to write there, A1001. We change this to a 1, and that would be game mode. We change to a 0. That's 0 is game mode, 1 is dev mode. Okay. So LDA 80, STA A1001. Now we're gonna have to, we'll just give it a shot to do a jump indirect, but we have to read the we have to read the reset vector and store it into SRAM. Okay, so, but we've got the reset vector should be visible now. So we need to do an LDA absolute. What we should do is there's a this might be a little bit easier than writing it by hand. If this is what I think it is, but it's taking forever, I don't know. This is it. So here's what we do. LDA 8000. It could be 80 is game, 81 is dev, STA A001, MMC3 program protect and bootloader select. LDA FF FFC I just know that I'm gonna I forget. Well, we'll have to figure out what address that is. And then LDA FFD STA 6000 X jump 6000 wherever that happens to be. So the address of this, let's just do this 1011. I guess it doesn't. Oh, this is indirect, so we can just. We could do a jump absolute, or we could do a jump indirect. It'll be easier to do a jump indirect because then we can add code here, and this is where's my hex dump? How come it doesn't? Oh, here it is. We might need to give ourselves a few more bytes here. Okay. So any reason not to do? Oh, you're right. You're right. Good call. Yeah, we don't need to do that at all. Just jump. I'm used to thinking about indirect only really being useful in SRAM, but that's not the case at all. Ordering my dinner here. All right, so jump FFFC. Just that. Yeah. But assemble that. Hex dump. That's all we need. Hopefully. 1, 2, 3, 4, 5, 6, 7, 8. So that's an 8-byte. Now this isn't very we need more code that reads the controller and then decides which value to write. But if we get all this right, we should be able to just change this 1 bit of our memory initialization file and our game will boot to one or the other. Yeah, so A980, 8D01, A0, 6C. So this is the jump indirect opcode FC FF. Right? Yeah, I think so. And our reset vector is 6000. So we've written that. Now we need to We need to redo our core generator here. IP core. Redo this. 8192. 8 bits. Uses all 4. Got that right. Our memory initials. So this is bootloader force game mode. Right? Yeah. Override our initialization file. I think they're already in the project. Yeah, there's some different data there than our previous one. So let's hope that's right. So let's flash it up. Yeah, the indirect is going to jump to the address stored at the reset vector location, which is precise. So we really don't need any RAM. I was thinking we were going to need one for the indirect jump, but no. I mean, we need the RAM for the bootloader, but really it's just ROM. All right, so we'll test it with the Ion Retro here quick. Well, that's not good. It looks like it didn't. It's reading the FF again. I wonder. Did we synthesize? Maybe we didn't. I think we forgot to synthesize. We did the IP generation, but we didn't actually synthesize, I think. We'll see if our checksum changes. But I think we just forgot. So our code changes in our game mode forgot or didn't get in. B9AE, or maybe I missed it. We'll see. How about now? Okay. Yeah, that's probably good. Our reset vector is actually that. Yeah. Okay. Think it'll work. Moment of truth. Hey, it worked. All right.
Make your selection
now. Let's do this. See if my MMC3 IDEO works. Let's switch it back over here. So write this to bootloader force dev mode.mi. What? Let's just add both these guys. So the dev mode is 8.1 and the game mode is supposed to be 8.0. Okay. So redo our IP core generator. Sure would be nice if you didn't have to, or at least remembered what you did last. Dev mode. Yes, I'll write those files. Okay. Synthesize that. Oh, you know what? The checksum might not have actually changed if the checksum only is a checksum of the configuration data and not the RAM initialization data. So I'm less certain of this working. But it might. All right. I don't know if this works. Maybe I got enough in me to try the controller read code. That looks like the dev ROM. Well, yeah, of course it is. That's what we were, I mean, anyway, okay. We're not, the INL Retro isn't actually executing from the bootloader ROM. I could have read the value to make sure that it was that one bit that we changed. But here's moment of truth with bootloader ROM, or the dev ROM. Oh. Oh. Why did it work on one power up but not the other? I don't know. Not sure what's going on there. Hey, homebrew, how we doing? Yeah, RNG dev cart. Why is it? I wonder if we're not preventing bus conflicts properly. Sometimes you get one, sometimes you get the other. What is... could be a bus conflict issue. Whether or not, let's with our level shifter and stuff, let's read which byte is that go back to our, so it would be 6003, or no, just 6001. Well, didn't we already read that? Oh, we read it down here. Oops, why did I unplug that? Wrong thing. So it is 8.1, which should be selecting the dev cart mode, which sometimes works, other times not. If we can't easily figure this out, we're just gonna have to kick the can to next time, but let's see. Let's look at our so if program is 1, then certain cases we're going to read from the cart. Otherwise, it's always going to be into the cart. But are we maybe improperly enabling the block RAM output? Because the block RAM is controlled up here, our buffer. So our FPGA is going to output data on the 3-volt data bus if block RAM output enable is low. But that should only happen so this is our bootloader mode. So if we're in bootloader mode, CPU address 1314 high, M2 and ROM selector high, so we're in the 6000 RAM range. We'll enable the WRAM chip enable. If ROM select is low, or if WRAM chip enable is low, will enable, so that gets us from the whole 6000 to FF range, enabling the block RAM. Now, if W chip enable is low, then we're in the 6000 range. For a write, which this is what should be active here, block output enable is high. Write enable is low. Else block output enable low for a read. Yeah. For the program space, and this is what happens. Hey Deedle, how we doing? Trying to figure out why my dev cart is random. Dev cart mode, or I think I've got a bus conflict issue, but I don't actually know. If read write is low, then we're writing. Oh, yeah, so if 6000 range this, else we're in the 8000 range and up, it's always going to be, if we're writing, it's always going to be disabled. Otherwise, it's going to be a read, and output enable is going to equal ROM select. So that looks right. But and on top of that, both the program and both programs are going to be disabled in this bootloader mode. And when if this program is, so this is when we need to read from the 3-volt flash. If the TSOP 48 chip enable is low and our output enable is low, we read, we're out of the cart. One thing that I kind of like it to be that, to where the level shifter is only enabled on the second half, or the end, the later portion of the 6502 cycle. If block RAM is enabled and it's being read from, then we will also have it out and enable. I don't think that's going to fix our problem. I feel like there was one other place I wanted to check. Oh, I wanted to check when we write to the mapper select register. 1 second. Is ROM slow opposite of CPU A15? Otherwise, it matches. Not 100%. So, the definition of ROM select is when A15 is high, ROM select is an inversion of M2. Else, if ROM select is low, it's high. So for a 6502 access where A15 is high from 8000 up, ROM select will go low at the end of the cycle to enable the program. If it's reading from below 8000, it'll stay high for the entire cycle. So if we go back to this code here, so in bootloader mode, upper bit of map select is low. We're disabling both the programs. If CPU A1314 is high, M2 effective, so this is M2 slightly delayed because of that logic of ROM select is always slightly slower, the propagation delay of the gate on the motherboard. ROM select will follow M2. So there's a brief period of time there where you actually don't know what A15 is because you have to wait to see what happens to ROM select. So if I delay M2 positive edge, then we don't have to worry about that. That's why I use this M2 effective. So if M2 effective is high, then we know now we're at the end of the cycle. We can use ROM select to determine what the state of A15 is. If A15 is high, ROM select will be low, which would be this case where I'm saying that the WRAM, the right portion of it, is disabled. If I might have just said that wrong. If ROM select is high, then we know that the A15 is low. So, and because we know this, and then we know we're in the 6000 range. So I'm going to enable the WRAM, what I'm calling it here. If ROM select is low, then A15 is high, and we won't enable the WRAM. So here I'm going to enable the block RAM from the entire range of 6000 to FF. So it's either in the 6000 range, which is what we just initially created here, or it's in the 8000 through FF. We'll enable the block RAM. Otherwise, it's disabled. Yeah. This is our 6000 range, writable. Otherwise, we're reading. If we're in the if ROM select is low, or I can't even talk. WRAM chip enable low. We have a write or a read cycle. Otherwise, it's not low. And we can, if it's a write cycle, this is always the case. If it's a read cycle, we'll enable it. This might be, is this complete? I think so. Anyway. I'm not convinced that we fixed anything. But we'll give one more shot here. I didn't check to see if, I mean, that when we had our block RAM, had this bit set, or this bit clear. I only tested it like once or twice. Possible that it randomly, but if the game mode always works but the dev cart doesn't always work, then it's like a 0 is preferred for whatever reason. That's why it kind of made me think it might be blocker, or it might be an issue with the bus conflicts. All right, so let's flash this guy again. And then we'll do a recap and call it a day. I'm done skis. Let's see what the INL Retro says here, just for confirmation. Yep. So the second byte of RAM is 8.1, so bit 0 is set. And it seems to be, and here we're selecting the game dev mode with writing 0.1. I was gonna say it could be some MC3 weirdness, but you wouldn't think that it would either crash or I'd get the game. I wouldn't get the game to boot. So let's switch it over and see what happens. Yeah. I'm gonna try one more thing. I've got this silly extender thing that I was using for some dumb reasons I'm not going to get into right now, but okay, dev cart, that might be it. Oh, there it went into X53. Could be related. Oh, that's weird. So I tried hitting reset. It should only be writable once. So I'm going to power it up. Dev cart, and what's supposed to be happening is supposed to be going in dev cart mode like that. I'm going to try reset. I lost my kick. Seems to be, but for some reason, see if I can get Action 53 to go. I don't know, now I can't get to do it. I don't know. It just seems to work now. Not confident there. There we got the X53. I'm going to try to reset it and see if it earlier I was resetting. It should really not be able to get back to the dev cart mode.
Make your selection now.
Why does my reset button not seem to work? I don't know. Got some weirdness there. I don't. Yeah, it might. I also added this code, which is just kind of normally what I do if I want to like ensure that like I just don't know, man. Anyway, let's call it a day. We got things mostly working. Some weirdness, not quite sure about. Would be interesting to maybe get a oscilloscope on there and look at the signals a bit. I might get some I might be able to see, you know, indications of some bus conflicts or what, but anyway, yeah. So this is a recap of NESnet stream 16. Last stream we got our block RAM mostly or halfway working, and this stream we set out to actually implement our switch between the two different programs, and we were pretty successful in that. So let's switch it. The main thing that we're trying to do here is put a bootloader of sorts into the block RAM of the FPGA. So when the 6502 boots, it starts executing code on the FPGA. That code will sense the state of a controller and decide whether it should boot in game mode, which is the default, from the 3-volt flash, 2 megabytes, or if it should boot in dev cart mode from the 5-volt program. And the FPGA, it needs to have different mapper modes depending upon which state it's running in. So we mostly got that working. We had to break up the verilog. We made a new top Wi-Fi mapper module, and we separated our modules. So we have a game mapper module that we're instantiating here, and this is our Action 53 mapper. And then we have a dev cart mapper, and right now we just selected an MMC3. And when we're in that MMC3 dev cart mode, we enable the the 5-volt program, and when we're in the game mode, we enable the 3-volt with the Action 53. So we've got the modules down here at the end of the code for all of our different mappers, and then we had to create a switch basically. So the inputs always go to both mappers, but the outputs, depending upon if we're in game mode, right, we take all of the control signals from the Action 53 mapper. If we're in dev mode, then we take them from the dev mapper. And we kind of need, I mean, not kind of, but we do effectively need a third mapper, which is the boot mapper, of having block RAM visible. And all we really, the way we have it set up is the, if we, it helps to kind of see this, we put, so the block RAM, when the mapper first powers up, this block RAM is mapped all the way from 6000 to FFFF. It's only, the RAM is only writable in 6000, and then we have a mapper register in 8000 and above. So we can, and maybe one thing to do would be to move this around, this bug that we're having, but we only allow one write to this mapper select register. The upper bit, both bits start off at 0. If the upper bit is clear, we allow a write. And we're always going to set the upper bit so that we can't come back here again. And the lower bit is going to be whatever the CPU writes on bit 0. So being 1 or 0, we'll select which program gets enabled. So that lower bit controls which mapper, controls a big mux to select between the two. And then we had, this is just our control logic for the block RAM in that bootloader mode that we start up as. And we cut out the M2 duty cycle is 5 out of 8. That means it's high for 5/8, or it's M2, also known as Phi 2, is it starts low and then it goes high. It's high for long, so it's like the first third of a cycle, or 3/8, I guess. I think of it as the third, but technically it's 3/8. The first 3/8 of the cycle, it's low, and then it goes high the last 5/8. And ROM select is the opposite. When A15 is high, it'll be high for the first 3/8, and then it'll go low for the last 5/8. So anyway, we mostly wrote all that up, and we did some testing with INL Retro to make sure that both modes were working. And right at the end, we took a stab at actually writing the bootloader that was going to be in that block RAM. Kind of annoying right now, because to change the initialization value of the block RAM, and we tinkered with this last time, the best thing we really have is changing this text file. We don't, thankfully the code doesn't need to be that long, so we just do some copy pasting. I went ahead and I was writing it by hand, but I knew I was gonna probably mess something up, so we just used the Easy6502. And so this is what our bootloader actually looks like right now. It's only like 8 bytes, something like that. So LDA immediate, either the lowest bit is what matters for the mapper select, but because of MMC3, I actually set that upper bit and STA. Really, we could we can write anywhere 8000 and up, but I chose 8001 because this is actually writing to the program protect register on the MMC3. So if we're jumping to dev cart mode, we need to get that WRAM enabled so that we can execute our next opcode, which is just jump to the vector, jump to the reset vector, jump to the address at FFFC. So you can just do a hex dump, and this is our bootloader here. All of 1, 2, 3, 4, 5, 6, 7, 8 bytes. We did have to. The only other piece of that is we need the reset vector, which is right here, the second to last 16-bit word, because reset vector is at FD. So we're gonna put that code that we wrote starting at 6000. So we need to jump there after reset. So we copy that over to our memory initialization file, our 8 bytes, and synthesize it up. So right now, this is the one that we have flashed onto the cartridge. A9 LDA 80. So the lowest bit is clear, which should be dev cart mode. And I'll show it here quick. It'll probably behave itself. Where'd it go? Getting a little bit of weirdness where sometimes it boots in game mode. I don't exactly know why. But that's what it's supposed to do. So this is just the test ROM that we flashed to most of our boards that Pino Badge wrote for us. But it just does a quick test of the map. It senses the mapper and does a quick test. So it sensed that there was MMC3. And with the mirroring, it checked how much PRG-ROM was present, 512 KB. It did a quick, it's actually doing a memory test during that time. So it did a test of the program and sensed that all 8 KB was fine, and it did a test of the CHR RAM. My TN-ROM file only by default provides 8 KB just because that's how the original was, but I did a test of that and everything's good. So it's working. But sometimes when you power it up like I did just there, the write occurred. Otherwise it would have crashed. Presumably.
Make your selection now.
Because the write has to happen to get into Action 53 mode. To game mode. But sometimes it doesn't go into dev mode. I don't know why yet. I thought it might have been my little extender board thingy, but if I hit reset, I don't know, my kick drops out. Huh. It could be something to do with my kick. I'll have to think about that some more, because my kick lockout chip is actually controlling the FPGA. If the register write failed, we'd still be in bootloader mode, so the reset vector would just make it try again, right? Well, that's a good point. That is a good point. So it'll just keep trying over and over and over again. It wouldn't actually crash if the write failed. So I mean, I guess that's a good thing overall. Yeah. So maybe the write's failing, and that would be, you know, connecting up a logic analyzer and or oscilloscope and getting that might give us some indication. So our write's not always working. Sometimes it seems like so we'll go ahead and we'll change it to game mode, and it seems to all if we set it to game mode, that always goes to, I've yet to tell it to go into game mode and it went to dev mode. So this is kind of what we have to do. It's a little annoying, but if you want to load up a different ROM, you have to rerun the IP core generator, and we will force game mode. Let me just check it. Yeah, so 8.0. Overwrite the file. All right, and then we'll resynthesize and flash the board here. But I'm wondering if it's interesting that the write is allowed again. And that makes me wonder if my microcontroller is reinitializing the FPGA, which would get into my STM8 code. I'm not sure about that off the top of my head. So that might explain why the write is allowed again. Because hitting reset, it should just boot. You know, that write shouldn't be allowed to happen again, and it should be stuck there. But if my microcontroller is reconfiguring the FPGA when it resets because of a kick, then that might be, or it might just be my power and reset buttons are just kind of faulty. And oh, I forgot the switch here. So we just changed the 1 bit in our block RAM bootloader and power it up here, and we get action 53. It seems that we always get it. Oh, there we got the dev cart. So it seems to be more stable this way, but there we just got the dev cart. Anyway, we mostly got it working. It's kind of random which one you get. So have to figure that out next time, or maybe I'll figure it out in the interim off stream. And then the other thing to do would be to have it based on controller state, but really we want to get that stable first, just based on the bit that's written to the mapper select register, and it shouldn't change after reset because that register should only be writable once. Yeah. This write should only be allowed if map select upper bit is 0. Once it's 1, it shouldn't be writable again. Anyway. That's where we're going to leave that. And yeah. So thanks for everybody joining in and helping out. Keep me company. Right. Yep. We want to make sure that that's stable, and then we'll certain of that, then we'll move on to the controller read code, but it should be fairly simple to do. For any of you watching this on YouTube on my recap, you can always join us on our Twitch streams, which I usually start sometime Friday morning, afternoon here in the States. But yeah, so we'll catch you guys next time.